Okay, it's about that time. Let's go ahead and get started. So in the past many lectures now, like not even just the last lecture, we've been building up a lot of neural nets. So first, I think around lecture 6, we introduced neural nets. We'd sort of built on linear regression and logistic regression, and we built up to neural nets where we transformed the features. And then we developed convolutional neural nets not too long after that. As a way to deal with vision style problems. Then we developed recurrent neural nets not too long after that as a way to deal with things with sort of an inherent, maybe time structure or recursion structure, something that you might see in language, for instance, where you're building up words. And so I think at this point, you could really reasonably think, based on the structure of the course, that the whole course is building up to neural nets, and neural nets are like the epitome of machine learning, and that's all you should ever use for every machine learning problem. And part of that sentence is correct. So there's a very real sense in which it's natural to build neural nets from things like logistic regression. They add extra elements like learning features. It's natural to build convolutional neural nets and recurrent neural nets from when we've learned about neural nets. And these are certainly super important methods. They've really revolutionized a lot of applications, especially in things like vision. We might use a lot of these ideas in maybe natural language processing. But what's incorrect about my previous statement is that you should use these on every machine learning problem. It's more realistic to think that what we're doing is we're building a toolbox, and these are part of that toolbox. They're very useful and important part. But there are other aspects of that toolbox. So just because we did linear regression and logistic regression first doesn't mean that only silly people use them. Absolutely, people use them all of the time to this day, and to great effect. And we're going to see today some more elements, some more machine learning tools that should probably be in your toolbox as you go forward. In particular, if you care about interpretability, decision trees are a really important part of your toolbox. And if you care purely about predictive performance, then ensembles and random forests are a really important part of your toolbox. So we'll spend some time talking about each of these methods today. Okay, so first let me just spend a little time hopefully convincing you that predictive performance isn't everything, that there are things that we really do care about beyond pure predictive performance, or perhaps we just need to rethink what we mean by predictive performance. But an example of this, I think, is very timely. It's election audits. So if you looked in the news very recently, but here's actually an article from back in October, even before the election. Election audits are a very important item that people are talking about. 46 states, at least according to this article in October, have some sort of auditing regime in place to just double check if there is some kind of user error or some kind of like technical glitch or whatever. But this isn't a new idea of auditing elections. So here's a paper from 2008 that's been very influential. Actually, the news article on the left was talking to Philip Stark, who wrote this article in 2008 and has been doing a lot of work in election auditing. And I'll also mention Ron Rivest in our department here at EECS at MIT has also been doing a lot of work in election auditing. It's a pretty cool area and gets into some neat math. But here's a quote that I really want to excerpt from this 2008 article, which is the choices that this researcher made, he made them to simplify the exposition and implementation. His methods need to be transparent, to be adopted as part of the election process, and to inspire public confidence. He thought about using sort of methods that are more familiar to data analysts, and they might be more efficient. In fact, they probably are. But because of their complexity, they'd likely meet resistance from elections officials and voting rights groups. And so I think this is a nice explanation of, why do we sometimes need methods that maybe don't reach the absolute peak of something like predictive performance or some other notion of goodness. Well, it might be that we just need to explain them to people. And I think it's not just that, everybody's being silly and we should all accept neural nets as our new overlords. There are plenty of reasons that we should want these good explanations. I mean, one is that there are reasons to be skeptical of methods you don't understand. So lots of folks right now seem to say they have machine learning solutions, and maybe they're selling snake oil sometimes. And so, if you're not a machine learning expert, being able to distinguish between those items might require some kind of interpretability. But it's not just about, whether you have expertise or not. Even if you're a machine learning expert, you probably actually care about interpretability. So here, Here's an example you can read in this paper of a case where machine learning experts ran neural nets and also more interpretable models on this problem where they were kind of interested in what is the risk of death from pneumonia from patients. So this was in a medical context. And the interpretable model had a very clear step. If the patient, once they got all of their methods out, they have the neural net and it's like, okay, here I have a neural net, what do I do with this? But the interpretable model, like very clearly and precisely stated, hey, if somebody is a patient with an asthma, with asthma and pneumonia at the same time, then they have lower risk of death from pneumonia. And so that's the sort of thing that, even if you don't have a lot of medical expertise, but certainly if you do have medical expertise, you might think that seems pretty silly that somebody who has asthma would probably be at higher risk for pneumonia. And because they had this interpretable model, they could say, hey, something is going on here that's a little bit weird, let's dig into it more. And in fact, it turned out the reason that this was happening was that the patients with asthma and pneumonia were being admitted to the ICU because they were deemed to be such high risk. They got aggressive care that decreased their risk of dying. And so this is an example of something that you've seen earlier in this semester, Simpson's paradox. So you might want to, check when that sort of thing is going on. And now you are aware already from this semester of Simpson's paradox, but now you have an ability, maybe, if you have an interpretable model, to see that that might be happening. Another nice thing about interpretable models is that there's less room for human error. So if you look at Malcolm Gladwell's Blink book, there's an example of Dr. Brendan Riley, the chairman of the Department of Medicine at Cook County Hospital in Chicago. He was facing resource shortfalls. They have lots of poor patients that they're treating, and they needed a way to diagnose heart attacks in patients that were presenting with chest pains, who came in and had chest pains. It was quick and accurate. And so they end up using exactly the method we're about to talk about, a decision tree. But here, you could say they care about predictive performance, like they care about accurately diagnosing each person who comes in. But the problem is that the machine learning method isn't exactly the method that they're using. They're using a person using the machine learning method. And so, that's not the kind of thing that you're testing when you're testing cross-validation, when you're looking at test set error. That's actually an extra element of the system beyond the pure method. And so that's a reason, at least on the face of it, if you can't do more, that you might care about something that's very simple to use so humans don't mess it up when they're using it. Okay, so there are a lot of reasons to care about interpretability, about things beyond predictive performance. It doesn't even just have to be interpretability, although that's what I've been focusing on here. But even if you only care about predictive performance, you should care about today's lecture and you should care about trees, because basically trees are part of the things that have the best predictive performance in many cases. So if you look at this Kaggle, Kaggle is a subsidiary of Google LLC, but it also runs machine learning competitions, among other things. And there was this magazine that recently in March did an interview with a Kaggle master, ranked 19th in the global Kaggle competitions leaderboard. And what's interesting is they say sort of like, what's his toolkit? And if you look at these algorithms in his toolkit, Light GBM, XGBoost, CatBoost, these are all ensembles of trees. And so while neural nets can be really useful, again, for things like vision and NLP and so on, the reality is for a lot of the data that you're going to encounter, ensembles of trees are basically the thing that really does the best in terms of predictive performance. Okay, so at this point, hopefully you're motivated to hear about what is a tree and what is an ensemble of trees. And so that's what we're going to do today. Okay, so let's start with what is the decision tree? Well, a decision tree is basically just a presentation of a series of decisions in a tree. So let's start with that, and then we'll nail down exactly what it is. So let's say that I have something coming in. Maybe they came in with a heart attack. And we know after the first 24 hours whether they've had a heart attack, they've been in the hospital for 24 hours, and now we want to assess their risk in order to decide on their follow-up treatment. And so here is a tree that people actually, in sort of the early days of decision trees presented, which is the following series of decisions. So first we ask, let's look at a particular type of blood pressure, systolic blood pressure, over the last 24 hours and ask, was it, did it really dip down very low? Was it always greater than or equal to 91? So we have two choices, either yes or no. So if no, if it did dip down below 91, then this patient is considered high risk. If yes, then we're going to ask another question. The question is their patient age greater than or equal to 65? And patient who is a bit older might be riskier. So if this patient has an age less than 65, then we might just consider them low risk at this point. They're probably going to be okay. But if they're greater than 65, we have yet another question we're going to ask. Is sinus tachycardia present? For the purposes of this lecture, let's just say that this is a medical thing that you can measure and you can check. And you can check if it's present. It either is or it isn't. If it is not, then this patient is low risk. If it is, this patient is high risk. And so here was just a series of decisions, a series of yes or no questions that even if you don't have medical expertise, if you're provided with the appropriate data, you can just go through these and answer them. Okay, so this is like a nice little flow chart, but it's maybe not clear in this form how it relates to everything we've talked about in the class. So let's turn this into something that we can actually talk about in the words and the phrasing and the terminology of this class. Okay, so let's imagine in real life, we have a bunch of data. You can imagine each individual who walks in and is around for 24 hours after a heart attack is a data point. And we have various features associated with those individuals, like the date that they were admitted, their age, their height, their weight, was sinus tachycardia present, the minimum systolic blood pressure over 24 hours, and maybe their latest diastolic blood pressure. And maybe even there were some other features. Okay, so actually we can see each of these internal nodes in this tree as being some kind of cut or split on one of these features. So in particular, minimum systolic blood pressure over 24 hours, that's actually our 6th feature in this case. So we can write this as x6 greater than or equal to 91. Is this true? We'll go to the right-hand leaf if it's, or the right-hand child. If it's false, we'll go to the left-hand child. Okay, we can do the same thing with age. Age is our 2nd feature. So we can actually rewrite this as x2 greater than or equal to 65. If it's true, then we'll go to the right-hand child. If it's false, we'll go to the left-hand child. Is sinus tachycardia present? Well, this sort of depends on how we encode this. A typical way that we might encode, as we've seen, a binary variable, binary classes is either 0, 1 or -1, 1. Either case, 1 is probably going to be the yes. And so we'll ask, is x5 greater than or equal to 1? And so here now we have our decision tree in terms of our features. Now, typically, what we do here is we do some kind of classification or regression. Hopefully it's clear that this looks like classification, that we're trying to classify into 2 classes, high or low risk, and so we might give them labels. A typical thing we've done in this class is give them labels like 0, 1 or -1, 1. And so here we're doing that. We're having 1 be high risk and -1 be low risk. And so here we are. So we can change this into our labels. And so at this point, basically we have created a classifier, or in general, a predictor. And so let's just double check that that's true, that in fact this is a classifier. Oh, and before we do that, let's finish up saying like what exactly is a decision tree? What counts as a decision tree? Well, it's going to be a binary tree with internal nodes and leaves. The internal nodes, each one of them is going to be defined by a dimension index j and a split value s. So for instance, if I look at this node, so this is one of the internal nodes, I've color-coded the internal nodes here as being white and the leaves as being green. So this is an internal node. It has a dimension index that we're splitting on, that's j, in this case j is 6. It has a split value s that we're splitting on, in this case that split value is 91. And then it has 2 child nodes, and each one of them can either be internal or a leaf node. And then the leaf nodes, so this one's a leaf node, this one's an internal node. Now the leaf nodes are defined just by their label. So we get to a leaf node, that's the end. It's not going to have any children, but it does have some kind of label, and that's what we're going to predict at that label. Okay, so as we said, this is a classification tree. This is doing classification as its form of decision. And now we can say that we have defined a classifier, just like we've done in the past for logistic regression, for neural nets, for any of the things that we've been looking at. And let's just check that that's true. So here, let's suppose that we have a data point that comes in. So a person comes into the hospital. That person has a bunch of features associated with them. Again, the date, the age, the height, the weight, is sinus tachycardia present, min systolic blood pressure, latest diastolic blood pressure. And now we're going to ask ourselves, well, how would we classify this data point? So in order to check what does this predictor look like on our particular data point, we're basically going to run through the decision tree. So first we're going to ask, is x6, is the 6th feature for this data point greater than or equal to 91? So here's the 6th feature. In this case, it's 115, so it's greater than or equal to 91. So we say yes. So now we go to the next decision. Is x2 greater than or equal to 65? Is the person older than 65? And we check this person's age, it's 49. They're not older than 65, so we go to no, and now we're at a leaf. And so as soon as we get to a leaf, that is our prediction. In this case, it's -1. We say this person is low risk. Okay, so this is a classification tree. We can use it to make classifications. You'll notice that it does not have to use absolutely every feature. We're going to see later that actually features can repeat too. We can have things like that. But it is a binary tree of decisions, a finite binary tree of decisions that eventually gives us some kind of classifier. And of course, we can do the same thing for regression. It doesn't have to just be classification. So let's take a look at a regression tree. So here, instead of a medical example, let's have an example that we actually visited sort of way back when we were talking about neural nets. So here our example could be, when am I going to run? And how much am I going to go for a run? And maybe my two features that I use to decide this are temperature and precipitation. So how cold is it? And is it raining? How much is it precipitating out there? And my label could be kilometers run. Okay, so what are we going to do here? So we're going to again start with a decision. Say in this case, x2 is greater than or equal to 0.3. Basically, is there a lot of precipitation? In which case we'll go to yes. Or is there not so much precipitation? In which case we'll go to no. Okay, well, if there's a lot of precipitation, maybe it turns out that I just go inside and I go on the treadmill and I don't want to run as much. And so I run, let's say, 3 kilometers. If there's not so much precipitation, I'm going to ask, is it cold? So we'll have x1 greater than or equal to -5. And maybe I say, if it's cold, so if there's a no here, then again, I'm going to go on the treadmill. I'm not going to run maybe as long. Maybe it'll be 2 kilometers. If it's yes, maybe I'll ask, is it warm? Is it way too warm? Is x1 greater than or equal to 33? So if it's very warm, or if it's in sort of intermediate temperature, so it's not too cold and it's not too hot, maybe I'll go outside and I'll run a good 5 kilometers. And if it's very warm, I don't feel like doing anything, and so maybe I'll just run 0. So in this case, what's different between a regression and a classification tree, we're seeing that in the regression, all the decisions in the intermediate part are totally the same as before. The only difference is the labels are real value now. So this is like the difference between regression and classification in general, that you have a predictor that's real valued instead of a predictor that's just, one class or the other, or multiple classes is also fine. Okay, so something to note here, and this is not specific to regression or classification, this is generally true for these decision trees, that the tree itself defines an axis-aligned partition of the feature space. So let's dig into what all of those words mean by first seeing what happens when we use this tree. Okay, so first, before we get to the root node, first we have all of the feature space. So in this case, that's x1 greater than 0. Sorry, it's x1 any value, because we can have sort of any value in degrees Celsius. I mean, technically speaking, there's a lower limit to that, but basically all the allowable degrees Celsius. Then x2 has to be greater than 0 because it's precipitation. Can't usually have negative precipitation. And so we have some whole feature space that's here in orange. Okay, so now we're going to look at the first split here. So the first split is saying, let's look at x2 greater than or equal to 0.3. And so what we're doing with this feature space is we're saying, hey, we're going to split it into 2 parts with a line. So this is x2 equals 0.3, the line. There's a part where x2 is greater than or equal to 0.3, in which case we go to the right child. And there's a part where x2 is less than 0.3, in which case we go to the left child. Okay, now in this case, when we go to the left child, there's actually another decision, another split. And so when we're splitting, you can really think of the split as being applied to this feature space. We're actually making a split in this feature space. So in particular here, now what we're going to do is we're going to take only the space where x2 is less than 0.3, and we're going to split it with x1 equals -5. So you'll notice this line only applies when x2 is less than 0.3. It's like we've already restricted ourselves to the x2 is less than 0.3 space. And on one side, we have x1 less than -5, and on the other side, we have x1 greater than or equal to -5. Okay, so now, again, we say, where are we in the space right now? Moving down this regression tree. And then, I'm gonna finish this up and then I'll do the question. So then we have our x1 greater than or equal to 33 split. So again, we're gonna split up our space. So we have x1 equals 33. On one side, we'll have x1 less than 33, but it also conforms to all of the other constraints we've imposed so far. So this is the set right here where x2 is less than 0.3, x1 is greater than or -5, and x1 is less than 33. And on this side, we have the same first set of constraints, and then x1 is greater than 33. Okay, so the question is, how could regression trees generate labels with a continuous number when we have a binary split node? And so what's happening is that the binary split node is just partitioning the space, as we're seeing here. But the continuous value that you actually say is your regressor, that you actually say is my prediction at a particular point, is the value in the leaf node. And so, here I've got kind of lazy and I put those values as 3, 2, 5, and 0. If I had been slightly less lazy, I could make them more obviously real valued, like, maybe sometimes I run 3.2 kilometers and sometimes I run 5.1 kilometers. But the idea of regression is just that you are predicting a continuous value. And so as long as you are allowing, a continuous value in your leaf nodes, you are doing regression. Another way to think about that is what's happening in regression is that for every value in your feature space, you are predicting a continuous value. And so what we're actually seeing here in this little plot that I put in the lower right-hand corner is our feature space. And if you think of this as being a three-dimensional plot where sort of the Y label is coming out of the slides at you, then this would actually be, you could have that Y label and then you would have your regression values, which in the case of orange is 3, in the case of red is 2, in the case of blue is 5, and in the case of purple is 0. And so if we could imagine rotating that, and then you would actually see this sort of step function that we're predicting. And so the difference with classification is just that you're only allowing in the case of 2-value classification, those 2 values, but if you were doing 3-value classification, multi-class classification, you wouldn't be putting that on a Y-axis. You would be saying it's like A, B, and C is what you're predicting, and you wouldn't just plot those on the same thing. Because as we saw before, having, this is back in lecture 3 with our features, we saw that having multi-classes isn't the same as having an ordering like 1, 2, 3, because there's no ordering on those classes. And so that's where I think you can really see that there's a difference in what you do with the classification and regression. Now, that being said, I think this observation about the binary split node is key because it tells you that we're really doing a sort of simple type of regression. We're not getting a really different prediction from one point to the next. We're really doing a step function as our regression. Now, I said in the beginning of this slide, or earlier in the slide, I would say, what is an axis-aligned partition? So let me just say that now. So a partition is when you have a bunch of mutually exclusive and exhaustive sets. That is to say, the sets are all separate, they don't overlap, and when you take their union, they all become the whole space. And so that's what we're seeing here, is that we've taken up this space of x1 and x2, our feature space, and we divided it up. That's all you're doing in a partition. You're dividing it up into little, subspaces. And so we have basically 4 here is what we've done. And in each one of those, we're going to predict something different. Now, 2 things that are worth noting about this. One, this is why we end up getting this step function, because we're just, in this case, predicting a constant value. Now, you don't have to do that in regression trees. You could do something else at the nodes, but here we're just going to do a constant value. The other thing to notice is that these are axis aligned by our choice of splits. Our splits are, we take one dimension and we split it a particular value. And so we're always going to get these lines as our dividers that are parallel to one of our axes, like x1 or x2 in this case. Again, that's something that you could try to go beyond. That one's a lot harder to go beyond in a reasonable way that actually gives you useful predictions, but it is something that you can do. Great. Okay, so now we've talked about 2 different types of decision trees. We've talked about classification trees, we've talked about regression trees, And in a way, you can think of what we've done so far as being describing the sort of forward mode of these. You know, we talked when we were talking about neural nets about sort of the forward run of the model and then going backwards through it. And so here what we're doing is we're saying, hey, if I have a decision tree and I have a data point, I can tell you the prediction. I know how to do that, and we've talked through that now. Okay, and that's step one of our familiar pattern. So at this point, hopefully this is becoming so old as to be boring. You totally know the familiar pattern and you're really familiar with it. So step one, we have to choose how to predict a label. So if we're given a set of features and a predictor, which is defined by parameters, and we'll say in a moment, you know, what is a natural way to think about parameters here. But given features and parameters, we know how to predict a label. So we just saw that with decision trees. We looked through an example and the medical example of, suppose I have a data point, you know, what'll I do to predict whether this person is high risk or low risk? We could do the same thing here. You know, if I have a day that is 20 degrees Celsius and there's 0 precipitation, I can go to the top, I say there's 0 precipitation, so I go to no. It's 20 degrees Celsius, so I'll go all the way down to the bottom and I'll say I'm gonna run 5 kilometers. Okay, so we know how to predict a label given a set of features and parameters. The next thing that we do is we choose a loss between our guess and our actual label. So we'll just do that in a moment. Of course, that will depend on whether we're doing regression or classification. That will depend on what type of thing we're doing with regression and classification, but it's something that we'll choose. And then finally, we somehow choose parameters by trying to minimize the training loss. Okay, so what are the parameters here? Well, the parameters are typically the thing that, you know, describes what is our predictor. And so in this case, we have a bunch of unknowns. We want to say for each internal node, what is the split dimension? We want to say for each internal node, what is the split value? So again, for x2 greater than or equal to 0.3, the split dimension is 2, the split value is 0.3. So those together will define what's going on at that internal node. What's my, you know, what am I gonna do? How am I gonna make my decision? But I also need to say, what are the 2 children nodes? Is there one leaf and one internal node? Is there one internal node and one leaf in the other direction? Are there 2 leaves? Are there 2 internal nodes? These are all possibilities. And we need to say which it is. And then for each leaf node, we have to say the label. So what we're gonna do in a moment is we're gonna come up with a way, once we've chosen a loss, to choose all of these parameters by trying to minimize the training loss. Now, something that's worth noting here that's a bit different from things we've done in the past, hopefully sort of immediately different if you think back to like linear regression or logistic regression, but actually really different from most of the things we've done, is that the parameters here don't have a fixed dimension. So as soon as I make an internal node, if that has 2 children that are internal nodes, now I suddenly have a bunch more parameters. And if they have internal nodes as children, now I have a bunch more parameters. And in fact, you can get more and more parameters this way. So that's a bit different than what we've done in the past. Okay, so let's suppose that I'm going to do regression. I'm going to choose to do regression. And I'm going to choose squared error loss, because that's a really natural thing that I might do for regression. Well, hey, squared error loss, we've talked before about how, you know, if I were doing, you know, something with squared error loss, I might, in general, try to set up everything in my problem so that's all differentiable and run gradient descent or stochastic gradient descent. And that's just not going to happen here. So a couple of things to note. One, we certainly haven't talked about how you would do gradient descent or stochastic gradient descent if you don't have a fixed dimension parameter. That sounds like it might be hard. 2, this is definitely a super not differentiable structure. So if I'm trying to decide whether to add an internal node or not, that's, at least on the face of it, not differentiable. That's just a very discrete decision. And so it's really not clear that I could apply something like gradient descent or stochastic gradient descent, which really relies on there being differentiability in all of my parameters, that my loss, my overall objective is differentiable in all my parameters. And so we're going to have to think about what could we do? Well, we could go back to our roots, you know, way back at the sort of very beginning of this class, we used a heuristic, the perceptron. We don't always have to use gradient descent and stochastic gradient descent. I mean, even when they're available, we don't always have to use them. And so in this case, we're going to look at a heuristic. It's going to have 2 parts. We're going to build up a tree. We're going to think of it as growing the tree, and then we're going to prune it back. So take away parts of the tree. This is a particular way. It's a very classical way to build a decision tree. I kind of want to emphasize that just like many things we've talked about in this class, this is not the only way to make one. There are definitely other ways you can make a decision tree. And I think in some ways, what's really important to understand is the simplicity of the ultimate decision tree that you get is very useful. You know, it's very understandable. It's the kind of thing that you could present to somebody who's an expert in another area, who isn't an expert in machine learning. You know, you could have an extremely smart medical practitioner, and that doesn't mean that they know about neural nets. So this is something you can easily talk about with them. If you're serving on a jury and you're participating in your civic duty on a jury, a tree is something that you could explain to your fellow jury members. And so that simplicity is separate from what we choose to learn it. And now we're going to talk about, here's an algorithm that you might use to learn it, but again, not the only thing you could do. Okay, so again, we're going to talk about these two steps, building it up and putting it back. Okay, so let's first start by talking about building a decision tree. And as just a motivating example, let's imagine that we have some toy data over here. And it is running times based on the, again, temperature and precipitation. So X1 is the temperature. When it's very cold, maybe I'm not running. When it's very warm, I'm not running. And then X2 is the precipitation. When it's precipitating a lot, I'm not running. But when you get that nice temperature and there's not a lot of precipitation, then I'm running, and maybe it's something like 5 kilometers. And we're going to think of this as a regression problem. Again, if I put a little more time into this, these could be numbers like, realistically, I might run like 5.2 kilometers or 4.9 kilometers. So you can think of these as being, values that really do vary continuously, and we're trying to learn a regression tree. Okay, so if we're trying to learn a regression, again, a really natural loss is squared error loss. So let's just go ahead with squared error loss for the moment. It depends on what you're trying to do in general, and it's not always the right choice for regression, but for here, it's certainly convenient, and we might just go ahead with it. So let's suppose we're building a regression tree with squared error loss. Okay, so we're going to build our tree, and it's going to take 2 inputs. One, it's going to take a collection of data indices. What do I mean by that? Well, the first thing that we're always going to do when we run build tree is we're going to run it on our training data. And so here, the collection of indices that we put in, will be the indices of our training data. Training data point 1, 2, up to n, assuming we have n training data points. Now, why would we bother making that an input to build tree? Well, the problem is we're going to be doing it recursively later with just a subset of the data. And so that's why we want to make that an input. We'll see that that's important as we go along. Okay, next we have k. So k is going to be sort of a hyperparameter of this algorithm. It's going to be the minimum number of points that we allow in a tree branch, or in a leaf. So basically, as soon as we get down to 2 points, we're going to stop. We're going to say we're done. We're not going to go down to allowing a leaf with just say 1 point in it. Or actually, I should say this is, according to the algorithm we're about to build up, I think it's actually the maximum number that we're going to allow. I take that back. Yeah. Okay, the point is we're not going beyond 2. Okay, so our first question, because we're not going beyond 2 points, we're not letting ourselves have more than 2 points in a branch, we're going to ask ourselves, okay, is the number of data points that we're looking at right now greater than or equal to 2? Okay, well, let's start asking that. This is a real question for the chat. I'm looking at the number of data points. When I run this, I'm gonna run exactly build tree 1 to n on the data set that I have right here. So this is a data set that I'm illustrating with the 0s and 5s. I'm gonna run this build tree. What is the number of data indices? So that absolute value I means the number of things in the set. So I'm asking for the chat, what is the absolute value of I here? What are the number of things in the set of indices? Okay, I'm getting great answers from both directions. So some people are answering in full generality, which is great. In that case, the answer is n. There are clearly n things in this index set. And if you did answer in full generality, I'll ask you to also think about what is the number n for this particular data set that we're illustrating here. Great. So just to recap, in this data set, just to be really clear about how I'm labeling things. So I'm at a particular X1 and X2 point. If there's a point, I'll put a number. And that number is the regression number. So it's like, oh, at this data point, it's the label, I ran 0 kilometers. At this data point, I ran 5 kilometers. And so the answer, which many of you are getting correctly, is 11, because there are 11 data points that I'm plotting here. And so I'm going to check, in this case, is 11 greater than or equal, or less than or equal to 2? And it is not. And so I would skip this if statement and the first time I run this build tree for this data set, but let's ask what would happen if I did happen to have actually only 2 points, and we'll fill it in. Okay, so if I only had 2 points, if I were making myself a leaf, well, what happens at a leaf? At a leaf, we just make a label. We just say, what's the label that I'm going to have? What's the predictor that I'm going to return for this little area? It'll turn out to be like that little partition element that we saw before, this little block of space in our feature set. Okay, so we're going to have to set y hat somehow. How are we going to set y hat? Where y hat is our label. It is what we predict in this little area. Well, remember, our goal here, I mean, this is going to be sort of a heuristic method, but our goal is to minimize the loss. And in particular, the loss or the error, the thing that we want to minimize here, is going to be the sum of the losses over the data points in this little set. So we have a sum over data indices in the tiny little set that we're looking at right now. I mean, by construction, it's tiny because it had fewer data points than K. And then we're going to have the loss for that data point. And so something that you should do is either immediately think that you have already solved this problem earlier in the course, or even better, solve it again right now. And by right now, I mean, if you don't immediately think of the solution, do this later on your own time. But you should convince yourself that the y hat that minimizes this loss is the average of the y's of the training data here. So this is a great exercise if, you know, maybe you're getting a little rusty on this from earlier in the course, but make sure you convince yourself that if I'm trying to minimize the squared error loss on this sort of subset of data, then I'm going to take the average of that subset. And that'll be, if I have to do a constant prediction, that'll be the best thing I can do. Okay, so now I know what I'm going to use for my label in this leaf. It's going to be the average of the data points that fall into this leaf. Okay, so now let's think about what happens if I didn't get down to, say, 2 data points, or if I didn't get down to, in general, K data points, which is certainly what happens the first time I start building this tree. Okay, in that case, I'm going to have to make some kind of split. You know, that's what happens in our internal nodes. I've decided I'm not making a leaf, so I'm going to have to make an internal node. And that internal node does a split. And so that split, remember, has a dimension and it has a value. And so, for instance, the dimension in this case, in this toy example we have here, could either be 1 or it could be 2. Those are the only dimensions that I have. I'm basically going to go through all my feature dimensions and consider each one of them in turn. Okay, well, let's suppose that I choose x1 and I choose a split value that's maybe slightly negative. This is what my split would look like. Or maybe I could choose a different split value, or maybe I could choose one over here. You know, any of these would be totally fine. Okay, so here's an issue. If I have a for loop over every data dimension, that's fine, because there are, you know, usually d data dimensions. That's a finite number, and we're all good. If I have a for loop over every possible split value, and these are continuous dimensions, I have an uncountable for loop. And that's bad. That's not something that I could do on my computer. And so that seems like a problem that we're going to have to resolve. And basically, I'm just going to come back to it in a moment, but hopefully you can think to yourself, why is this bad? We couldn't have a for loop over an uncountable infinity, or any infinity, really. Okay, so let's suppose for the moment that somebody just gave us our split dimension j and our split value s, and go forward with that. And then we'll come back and resolve this issue of, you know, how could we deal with the fact that we have seemingly an uncountable infinity of split values. Okay, so somebody just gave us, they said, hey, we're going to take x1 and we're going to split on a particular value s. Okay, what does that do? Well, it divides my data into 2 parts. So for instance, if this were so if I chose x1, so if my j was 1, and my split value s was where this line intersects the x1 axis, then I would have 2 sides. I have the side where xj is greater than or equal to S. So I'm going to call all the data indices on that side I plus. And I have the side where xj is less than S. And so I'm going to call all the data indices on that side I minus. Okay, so here's a question for you again for the chat. Suppose I do this absolute value around I minus. That is to say, I say how many data indices are in I minus for this split. How many are there? Okay, it's looking mostly pretty good. Let's just walk through what we do here. So remember, I minus is the collection of data indices for data points where xj is less than S. So that's what we're seeing on the left side of the split here in that orange rectangle. And if we look at the number of data points in that orange rectangle, it's 2. And so we're going to have 2 data indices in I minus. If we look at I plus, we're going to say how many data indices are in I plus, and you can count them up. In this case, it'll be the things where xj is greater than or equal to S. In this case, it's 9 data points. And as should be the case, 9 plus 2 equals 11, our total number of data points. Okay, so that's what I plus and I minus are doing. They're just saying what are the data indices on one side or the other. And now what we're going to do is we're going to consider, instead of just having one constant value that we predict for this entire space, breaking it into a prediction on one side, which we'll call y plus, and a prediction on the other side, which we'll call y minus. So on the I minus data, we'll predict y minus. On the I plus data, we'll predict y plus. And then what we want to do is we want to minimize the error. So this looks, I think, complicated at first, but it is literally just the error that we wrote before, which is for every data point in I, we take the squared error loss and we add it up. It just so happens that every data point in I either is in I plus or it's in I minus. It's only one or the other. And so we can break that sum over everything in I into a sum over I plus and a sum over I minus. And then we just have the squared error loss in each. Okay, again, just like we did above, you can actually convince yourself that we don't need to do anything fancy to solve for y plus and y minus to minimize this error. Because remember, we want to minimize the loss. We want to minimize the error. And once we have j and once we have s, we can just solve for the y plus and the y minus that minimize them. You can convince yourself that, again, those will just be the averages. So this is much like what we saw in the part above. Now we're just saying what we're going to do is over I plus, we're going to predict the average of the training data in I plus, and over I minus, we're going to predict the average of the training data in I minus. Okay, so that means if we have a split j, so if we have a split dimension j and we have a value s, then we know how to get the best predictions. Now we have to choose the split dimension j and the value s. And so what we can do is we can say, hey, for this split dimension j and this split value s, what's the error? What's the loss? And then we'll choose over all the different j's and s's, what is the error? Or what is the minimizing error? How do we get the smallest loss? And we can do that by just calculating EJS for each j and s and then looking at which one is minimizing. Now, remember, we had this issue, though, where we said, there's technically, an infinity of values, in fact, an uncountable infinity of values where we could split. And so what are we going to do? Okay, so let's look up at our plot again up here. And remember, this line, this yellow line is a possible split. So here's a different possible split. Here's a possible split. And with this possible split, we're saying, hey, we're going to put everything on the left-hand side into one prediction bin and predict the average of those things. We're going to put everything on the right-hand side into another prediction bin and predict the average of those things. So if I change my split from this to this between these two options, so here's even 3 options. If I change my split between these 2 options, do my predictions change on the 2 sides? So this is a question for the chat, yes or no. If I change between these 2 splits, or even these 3 splits, do my predictions change? Great, everybody's saying no, fantastic, we're all on the same page. The observation here is that while technically my predictions at a new data point might change with these splits. My predictions at the training data do not. They don't change at all. Because these splits are between two training data points. And so, I'm not changing anything about how the training data gets categorized. And I might think to myself, well, in that sense, those splits are completely equivalent to me because all I know about is the training data. I'm just going to say, hey, those don't have any real difference. Now, there's a whole bunch of splits that are between two data points. In fact, again, an uncountable infinity of things. So all of these splits are between two data points. So I might ask myself, well, I got to choose something. How do I choose between them? One option is to choose the most central of them. Say, I'm going to average the two x1 values of the two data points and just allow a split straight between them. That's one choice. But the basic observation that we want to make is that because all of these splits are somehow equivalent on the training data, I don't really have a way to choose between them, so I'm just going to try one of them. I'm not going to try every single one of them and try to compute the error every time because I know I'm going to get the same error, the same training error in this case. And so instead of going over every split dimension and every split value S, which would be literally impossible to do, what we're going to do is we're going to go over every split dimension J, and then maybe something like one split value roughly per data point. So we might say maybe we'll do, a split value everywhere that it could make a difference, everywhere that there is a unique training data loss. And that'll be about on the order of the number of data points. I say about on the order because you might do different things at the edges. You might have two data points that have exactly the same x1 value, but roughly this is, you only have to do something roughly on the order of the data. Okay, so now we've reduced this to a problem that you can actually solve. We're going to try maybe something like the central values between every two data points. And so finally, we have a finite number of split dimension values J and split values S that we're going to try. And because we have a finite number of them, we can look at the error or the loss on every one of them, and we can say which choice minimized that error or that loss. And that's where we're going to split. Okay, so finally, so what we did up top was we said if we had a small enough number of data points, then we were going to make ourselves a node. It happened to be a leaf node. And that leaf node is going to have a label. Here we said, okay, we didn't have a very small number of points. So we're going to make ourselves an internal node, not a leaf node, but an internal node. And so let's think back what defines an internal node. We've said this a couple of times already, but now we're going to start getting really precise. Well, an internal node is defined by a split dimension, a split value, and its two children. And so here, what we're going to do, once we've found sort of the best split dimension and the best split value, is we're going to return that best split dimension. We're going to return that best split value. And then we're going to build the children. So the left child, let's think, how would you build a left child where you're basically going to recursively do the same thing on the data points in the left side of the split. So in particular, we're going to build tree on a set of indices that are now smaller than the original indices we put in. We put in our indices I, and then what we did was we found a split described by J star and S star. We're going to take all the indices on the left side of that split and build a tree with them. And then we're going to, on the other side, take all the indices on the right side of the split, and we're going to build a tree with them. And the reason now that this is I sub J star S star is because we chose a particular split, this J star S, described by J star and S star. And so we technically, in some sense, computed these I's for every single J and S, but now we're saying, this is the particular J star and S star that we chose. It's the particular split dimension and the particular value. And so that's what we're going to use to split going forward. And so you can see, in this sense, this is a greedy algorithm because it only uses the information that we have right now, and it tries to minimize the loss immediately, even if that might not be the best thing in sort of a long-term sense. And by long-term, I mean over multiple splittings into the future. Okay, so let's run through an example of doing this. Let's build a tree for this data that we have on the slide. So we start by saying we're going to build tree with all the data indices, 1 to n. As you observed earlier, n in fact here is 11. And so this will be, we're going to build over the indices 1, 2, 3, 4, 5, up to 11. And let's suppose we chose our K to be 2. That's how many data points that we're going to allow in a leaf. Okay, so first thing we're going to do is we're going to walk into this build tree algorithm and we're going to start making ourselves some kind of node. We first decide whether it's going to be a leaf node, if we finally made it to a leaf node, or if this is an internal node. As we observed, 11 is not less than or equal to 2. And so in this case, we will not be building a leaf node, we'll be building an internal node. So we'll go to the internal node building center. Okay, so over here, we're going to look at every possible dimension. Again, that's every dimension of our feature space, in this case, x1 and x2, and we're going to look at every possible split value. Every possible split value that could even give us a different loss, a different error. And so really, we're just going to look at something like maybe between each 2 data points. Okay, so we do that. We find maybe the the split value that is particularly good here, and we're going to start building our node. So what makes our node? Well, the first thing is, what was the split dimension and value that we found? Maybe it was this one. So here, maybe we found x2 greater than or equal to 0.28 is a good split. And so on one hand, we have x2 less than 0.28. So when it's not too much precipitation. And on the other hand, we have x2 greater than 0.28, when greater than or equal to 0.28, when there is a lot of precipitation. So that's the split that we've done. And if you kind of look at it, this seems like probably a reasonable first split to have done for this data. It sort of chops off the most things that you can that are unique in an axis-aligned way. Okay, so we made this internal node, and so it's going to have 2 children. It's going to have a left tree, and it's going to have a right tree. And the thing to notice here is we're going to start by making the left tree, just in the way that this sort of pseudocode runs. Okay, so let's talk about how would we build this? Well, we build tree on the indices that fell into that region. So in this case, hopefully you can see there are going to be 8 indices that fell into that region. There are 8 data points that are in that region. And so we're going to ask, is 8 less than or equal to 2? It is not. So we're going to build ourselves an internal node, and it's going to have a cutoff. Maybe in this case, it happens to be 7.2. And so that might look like the following. So we have our left-hand side and our right-hand side from that split. And now what we have to do, again, is start by building tree for the left-hand side. Okay, what is that going to look like? Well, again, we go up to build tree, and we ask, is the number of indices less than or equal to 2? This is a question for you in the chat. Is the number of indices less than or equal to 2? Awesome, a lot of great things here. Yes, exclamation point, it equals 2, and so technically, that is 2 is less than or equal to 2, and that's sort of like the relevant thing that we're interested in here. And so in fact, we will make a leaf node at this point. And so let's go ahead and do that. What does our leaf node look like? Well, we're going to take the average of the data points at this point. That's going to be our prediction. Another question for the chat, what is the average of the data points in this region? Great, yes, as you've observed, this should be a particularly straightforward average because both data points are 0, the answer is 0. In reality, probably they would be, very slightly different from 0, but this is one that's easier to do some math with, and so the answer is 0. So we'll make that the label at this leaf. Okay, so now we go to our right-hand build tree. And maybe we find that a particularly good split is between all these 5s and all these 0s. So on the right-hand side, we have the 5s. On the left-hand side, we have these 0s. Again, this looks like sort of our, we don't run when it's too hot. We run when it's a reasonable temperature kind of split. Okay, so now we're going to build our left-hand tree. And something you'll notice is that even though everything is 5, even though we've perfectly, we have this great regressor for everything, that's not our decision about whether to make a set of leaves. The set of leaves is, or whether to make a leaf. Our decision is the number of things in this partition element, or is the number of indices less than or equal to 2, and it is not. And so we're going to we're going to do another split. Okay, so maybe we happen to split here into some 5s on one side and 5s on the other side. In this case, all the splits are equivalent. There's nothing that's better, and so you have to have some kind of tiebreaker, and maybe this is just where the tiebreaker fell. And so we'll predict 5 on this side, we'll predict 5 on this side, because that's going to be the average. And then we'll go back up to making our left-hand leaf up here, and maybe we'll predict 0 over here. And then we finally get to our original left-hand leaf. You can see that we're doing sort of a depth first kind of thing here. And in this case, well, again, we're going to have to divide because there were 3 data points. And so maybe we'll have one side with 1 data point and one side with 2. Okay, so we have created a tree. We have built a decision tree by doing this. We kept going until we got down to a very small number of data points in each of the leaves. Okay, so now let's take a look at this decision tree. You know, again, what it's doing is it's creating a predictor. It's creating a function of the features, and you can sort of see that. You can imagine that it's popping out of the slide at you in the y-axis, and it's 0 over a lot of this area, and then it's 5 in certain areas, and it's basically a step function. It's a step function that we are predicting. Now, an observation that we could make here is, well, we didn't have to keep splitting. I mean, at some point we actually had like 0 error. And so why would we keep splitting? You know, maybe we should stop splitting at 0 error. Maybe an even better idea is for regularization purposes. We could do something like stop splitting after our error gets quite low. You know, maybe we should just check if our error is too high or not. A related question here is overfitting an issue? And if you think about it, what we're doing here is we're getting down until we have 2 data points, and then we're fitting them as perfectly as possible. You can imagine if k is 1, that you get down until you have 1 data point, and then you just predict exactly that data point's value, because that's the average of 1 data point is 1. And so it certainly seems like it would be easy to overfit in this case. And so again, how about we regularize by stopping splitting after our error gets low? What if we do that? Well, just an observation about what could go wrong there. So we're going to pursue this idea of stopping splitting when there's no or a small change in loss. Just an observation of what could go wrong is, let's look at this example. Suppose instead that I run when it's really warm and there's rain, or I run when it's really cold and there's no rain. This doesn't seem entirely implausible. You know, this could be a way that somebody decides to run. And suppose that I wanted to use a decision tree, a regression tree, to learn that. Well, at least if my data were perfectly arranged like this, and actually we did see some data back in the features lecture, back in lecture 3, that actually could be arranged like this, just due to the way that we encode features. You're going to see that let's try a first split with this. Suppose we're building a tree. We go to our first split, we say, hey, you know, we have our set of indices, there are 4 indices, and we're going to try every possible split. And there is literally no split that improves the error in this case. Everything is just as good as if you had, you know, just this whole region and you were looking at that. And so if we stopped when there was no change in loss or a small change in loss, we'd stop right here. And yet, if we made a split, pretty much any split, you know, that was between data points here, and then we made another split, we'd get a perfect predictor, and it would be fantastic, and it would do really well. Now, if these things are sort of moved around a little bit, the idea changes slightly, but the idea is still there, that somehow there's this issue of if you stop splitting when your error is very low, it can be very short-sighted. Kind of the issue is that we're doing these axis-aligned splits, and so it might take a few to actually get to a good point, rather than just a single one. Like a single one might not represent the thing that you care about. So from that perspective, you know, we were greedy when we were building this tree, but maybe we don't want to be greedy in stopping building the tree, which is what would happen if we stopped when there was sort of no change in loss or a small change in loss. And instead, an idea that was pretty influential when it was introduced and continues to be used to this day is to build the tree, to grow the tree with this algorithm, but then prune it back. And so I'm just going to briefly go over what that might look like. Again, I wouldn't get too obsessed with any particular way of building or learning a tree, but I think there are some general ideas here that are important to keep in mind about, what can you get from a tree, what kinds of structures can you look at, and how you have to be sort of aware about how you're learning it. Okay, so let's talk about how to regularize. Now, you can think about this, as being encased in some kind of objective. Certainly, this is something that we've talked about in other cases, sort of throughout our course, that we have some objective that we're interested in optimizing. And typically it looks like the following. It looks like a loss over the training data plus some kind of constant times a regularizer. And usually the regularizer is like a penalty. It penalizes having some more complicated model. It makes you pay for that more complicated model. It makes you say that, the loss was really worth it. And so we've seen this before for logistic regression, for linear regression. A lot of times our regularizer has been this squared error loss, or this squared error on the, or just sort of squared, sorry, I should say just sort of a squared size thing. Like if we have a theta, we were taking this, this squared penalty on the theta. And here we're going to look at something a little bit different. So here we want to think, what are our choices for our tree? Well, training loss, that's pretty straightforward. We already said that we cared about squared error loss for our training loss. And so we can just rate squared error loss for the training loss. So that'll be straightforward. The constant's easy to put in. But what do we want to penalize? And I think, at least based on our discussions that we've had so far just now, a natural thing to penalize is bigger trees, bigger, more complex trees. And so we might say our penalty is going to be on trees that have more leaves. If you have more leaves, you have to pay for that somehow with training loss. You have to have a better training loss. Okay, so here's a way to express that. Let's just walk through the elements of this formula. So first, we're just going to say, what is the name of our objective? In this case, we'll call it C. It'll be a function of T. So T is the tree that we learn. It's the predictor that we learn. And alpha will be the constant that trades off the penalty and the training loss. Often in the past, we called this gamma. Okay, so first we have the training loss. So there's nothing new here. We're just summing over all of the data points that we have. We're looking at the loss between our guess, which is the predictor T applied to the features for this data point, the ith features, and our actual, which is the actual label for these data points, the yi. And we have our alpha that trades off our penalty and our training loss. And here we're saying the thing that we're penalizing is the number of leaves. We're trying to express our preference for trees that have a fewer number of leaves. Okay, so what would happen if we looked at our tree over here and we did this trade-off? Well, let's start, and let's call this the cost complexity of a tree T. So this is often what it's called. It's again, very similar to the objectives we've seen before. Okay, so let's look at our tree over here. And in particular, if we had our whole tree, it describes this whole space with a bunch of partitions in it. But let's look specifically at this little subtree down here at the bottom. So the subtree that's defined by the x1 greater than or equal to 18.3 split and its two children, the 5s. This seems like a useless subtree. It's not doing anything. If we didn't have this subtree, if we just had a single leaf that predicted 5, it would do exactly as well. And so if you look at this cost complexity, and you look at alpha equals 0, then there's no way to decide between this full tree and the tree where this subtree is replaced by a single leaf. But as soon as you increase alpha just a tiny bit, it could literally be any slightly positive value of alpha, anything whatsoever that is slightly positive, suddenly it's not worth it to have this tree. Because you are taking a hit of an extra leaf, and you could reduce that by getting rid of this subtree. And so as soon as you have this very slightly positive alpha, it is better to replace this subtree with just a single node, with just a single leaf. Because that'll be one fewer leaves, and so you'll reduce the cost complexity at no hit to the training loss. And you'll notice that this is the same over here. So here we have a case where there's a subtree, this internal node and its two children, where there's no change in the loss, the training loss, if we reduce this to just a single node. And so if all we cared about was training loss, then these would be completely equivalent trees. But as soon as we have this penalty and as soon as we have a tiny little bit of alpha, then it's better to just get rid of that subtree and replace it with a leaf. Okay, so the idea of pruning is basically to just keep doing this. So with pruning, what we do is that we sort of, you can imagine sort of slowly increasing alpha. So here we increase it a little bit beyond 0, we can slowly increase it. And as you increase it, eventually certain subtrees are not worth it. And you can get rid of those subtrees one at a time as they become not worth it. And you'll end up having a finite sequence of trees until you get to the root. Eventually nothing will be worth it. And it would be better to just have a single constant thing that you predict. And once you have this sequence of trees, you can run cross-validation on it to find a best tree. Okay, but the idea here, I think the really key idea to get is that this can perform a lot better, having the ability to have a little bit of a longer, less greedy procedure to create these trees can perform a lot better than if you just stop making the tree when it seems like you're not getting any benefit from it in a particular step. Okay, so at this point, we know a way to create a decision tree. Again, I want to emphasize that's not the only way. In fact, I think there's some really interesting work going on in terms of trying to have the interpretability of decision trees with the flexibility of other methods. So you could try to have your very powerful, method that performs really great in terms of predictive performance. And then what you can do is you can try to have a tree that represents the information in that, even if it takes a little bit of a hit in terms of understanding. And so there are lots of things that we can do here. Trees are really interesting nonetheless. Oh, before I move on, I'll just get this question from discourse. How do we choose the value k, or should we just make it pretty small to get a large tree and then prune? Basically, these are both great ideas. A typical thing that people might do is that they might get their very large tree and then prune. And in the pruning aspect, you don't have to care too much about k. You might still care about k just from a computational perspective. So if you think about your k as being 1, you're going to have to make a ton of splits in a very large data set to put everything into its own little bucket. And so it might be just easier and faster to use a larger k. So that's a consideration as well. So basically there are multiple considerations, even beyond our usual ones like prediction error, but also just sort of speed and ease of use. But absolutely, yeah, you can just make a relatively small k and then prune back to do the regularization. Okay, another thing that you can do you can think about this as regularization. You can think about this as just doing better, is you can ensemble. So just as we just talked about, maybe we could choose a really small k, and then we could make this really big tree and then prune back. You could also choose a really small k and then ensemble, and that'll do some regularization for you. It also just will turn out that this is a good idea, period, to increase the performance of your method. Okay, so in particular, again, just when we started off, we said we're going to talk about decision trees in terms of interpretation. Now we're going to talk about ensembling in terms of predictive performance. The general idea here is that using multiple machine learning predictors, even if they don't seem individually really great, will make typically a much better predictor. So you see this everywhere. So if you look at the Netflix prize back in the day, not only did all the top teams use ensembles, but literally one of the team names was the ensemble. So good advertising for ensembles there. If you look at basically any other competition, that tends to be the case. So the Macrodakis competition is a competition that happens regularly on time series data. They looked at 100,000 time series in their competition, and no individual method ever did that well. But when you had these big ensembles of lots of methods, some of which included neural nets, but that wasn't the only method, you got these great performances. And of course, it's not all just about competitions. I mean, in some sense, the point of competitions is to prepare us to do things that really matter in the real world. And if you look at the forecasts that people are using for both cases and deaths in COVID-19 right now, the CDC, for instance, is reporting an ensemble forecast. And so there's just this generally, sense that ensembles are giving us really the best predictive performance when we care about predictive performance. Okay, so there are a lot of ways to do ensembling. We're going to talk about one of them. So in fact, I mentioned in the beginning these Kaggle competitions and the things that people were doing there. It turns out that's actually a different type of ensembling, boosting, and I encourage you to check that out if you're interested in that direction. We're going to talk about bagging. And from this, we're going to get a sense of what an ensemble does. Okay, so this is just one of multiple ways to make and use an ensemble. Bagging stands for bootstrap aggregating, which doesn't really make much sense right now, but hopefully will make a bit more sense at the end of this slide, because then I'll say what that means. Okay, so what we're going to do is we're going to take our training data, and we don't have to be doing trees right now. We could be doing, just about anything. And we're going to create a bunch of fake data sets from our original data set. In particular, capital B fake data sets. And the way that we're going to make these fake data sets is for every little b, we're going to draw a new data set by sampling with replacement from our original data set. So what does this look like? So in our original data set, you think of our original data set as a bunch of colored billiard balls in a bowl. So there's a yellow ball, there's a green ball, there's an orange ball, there's a blue ball, and there's a purple ball. And then what we're going to do is we're going to stick our hand into the bowl, pull out a billiard ball, and that'll be the first data point in our new data set. So we choose each one of these 5 data points in this case with equal probability. Now the with replacement part is where we take the ball that we're holding and we put it back in, and then we shuffle it up again. We choose from every possible point, again, with equal probability. If we were doing without replacement, every time we took one of these balls out, we would put it over here outside of the ball, and then we would draw a new ball, and there would be fewer balls every time. In this case, there's the same number of billiard balls. And so we can keep doing this. We can draw our 3rd data point in our new data set, our 4th data point. Of course, we're going to get some, probably, it's very likely that we're going to get some repeats because we're just putting it back in and we're drawing from the same distribution. In this case, it turns out we got 3 repeats. And so we'll say that this is our new data set and it has its own indexing. It just so happens that a lot of its data points are the same as the other one. And so here, what I'm going to do is I'm going to change this to be our new data set, indicated by x tilde 1, y tilde 1. So we have the first data point in our new data set, the second data point in our new data set, the third data point in our new data set, and so forth. But you'll notice the first, 4th, and 5th data points are the same. And 2 and 3 are different. Okay, and so what we're going to do is we're going to make this new data set b different times. And the trade-off with b is that the more b you get, sort of better in some sense, but eventually it's just computationally difficult and you stop getting as many benefits. So that's the trade-off for capital B. We're going to make all these different data sets, and for every one of these data sets, we're going to train a new predictor. And because the data sets are random, because they're different every time, we imagine that our predictor is going to be slightly different. And what do I mean by predictor? This is like, we're going to make some regressor. Maybe in regression, we'll have a different, set of predictions for new, this is a function of the features, what is the prediction we make at a new feature? So that's what that function is. Okay, and then finally what we do is we combine the wisdom of all of these different predictors. So we imagine each of these different predictors is pretty good at something, and we're going to return some combination of all of their information. So for regression, a typical thing that we might do is we might average over all of them. So we're going to return a final predictor. So this f hat bag is like what we actually return at the end of the day, and it's the average of all those individual predictors on the little different data sets that we did. For classification, you can do something similar. You can take the predictor at a point as being the class with the highest vote count with some way to deal with ties. But basically, at every point, for every one of your B classifiers, capital B classifiers, you're going to have some classification. It's going to say what class it thinks it is. And so you can do a voting across them and say, which one's getting the most votes. Okay, this is a super simple idea. All we did was we randomized our data slightly, and then we got this way better predictor almost for free. I mean, you have to run some extra things, but you just have, a bunch of these predictors, and you already had some way to make predictors. And so now you're just running in a bunch of these fake data sets. And so this is bootstrap aggregating, and it is surprisingly effective. You can have some pretty bad predictors as long as they're just slightly good. They're better than chance. This can be really, really effective. Okay, so why is it called bootstrap aggregating? The bootstrap part is making all these little fake data sets by sampling with replacement, capital B times. This is an idea that is not at all specific to trees. It's not even specific to bagging. It's actually an extremely general and surprisingly powerful idea for how simple it is. I mean, maybe I shouldn't say surprisingly. Some of the simplest ideas are some of the most powerful. But that's the bootstrap part. And then the aggregating part is when we aggregate it all together at the end, and we take all of these different predictors and we make them into one super predictor. It's like, if you took the Power Rangers together and you made them into Megazord, this is what's happening right here. Okay, so that's bootstrap aggregating. There's nothing that is specific about trees here. You could do this with any favorite predictor. In fact, there's reason to think that neural nets actually individually are kind of unstable. Like, you can get really different results if you just change things slightly about your setup or change things slightly about the data. And so you could put them all together if you wanted to in this. You can do a lot of things with bagging. But of course, one of the things you can do with bagging, or it wouldn't fit quite so well into this lecture, is bag trees, bag decision trees. And so that is so popular that it's given a special name. A name that you are likely to encounter in life, which is random forest. At least if your life is full of machine learning, you're likely to encounter this. Okay, so random forest is basically bagging with decision trees with a little bit of extra randomness. It's not exactly bagging decision trees. And I'll point out where the extra randomness comes in. Okay, so let's just briefly talk through a random forest. So random forest, you do the same thing. It's just bagging. And so what we're going to do is we're going to go through all these B different bags, basically. In each one of them, we draw a new data set with replacement from our original data. So that's just like bagging. Nothing has changed from bagging. Okay, here's the part where we make this about trees instead of a general regressor. So when we were doing general bagging, this could be any predictor. Now we're just speaking specifically about trees. We're going to build a tree on the random data set by recursively repeating a number of steps until the node size k is reached. Okay, so first, now here's the part that's different from both bagging and decision trees. We're going to select M features uniformly at random without replacement from the D features. So we didn't do this when we were doing random forest before. If this were just, or if when we were doing decision trees before, if this were just bag decision trees, we wouldn't have this part. This is like extra randomness. And it turns out to be useful to decrease correlation between the different trees you're learning from. Okay, but you're going to select these M random features, a subset of your D features. And now you're going to do the usual decision tree thing. So instead of going over all the features like we did when we were making decision trees before, you just go over the subset, but you still pick the best split dimension and the best split value among the M features instead of the total D features. And then you build two children. So everything here is basically bagging, and then we do trees, and there's just this little extra randomness here. Okay, and finally, just as in bagging, we return the average for regression, or some kind of top vote for classification. So why is it called random forest? Well, it's clearly random because we have multiple sources of randomness. So there's the randomness in making the different data sets, and there's also the randomness in choosing the feature subsets. It's a forest because you make capital B different trees. And so you have a whole bunch of trees, capital B of them. Each tree defines a predictor, and then you average over all of those predictors to get your final predictor, your final regressor that you're going to return. And so the forest is just because it's literally a bunch of trees. Okay, and so to recap, the bagging part was that we drew all these different data sets, and then we averaged them over for regression or voted for classification at the end. The trees part was that we chose trees as our predictor. So we could have chosen something else with bagging. It's not specific to trees, but here we chose to use trees. And then the extra randomness was that we didn't just use any features as we would normally for trees, where we consider all the features. We just concern ourselves with these M uniformly at random features. Okay, so at this point, we have accomplished some of our goals. Our goals were to try out to see, could we come up with methods that were useful for interpretability that weren't purely focused on predictive performance. And decision trees, I think, are certainly that. If we go back to our tree that we saw at the beginning, again, the hardest part, I think, in some sense about this tree is understanding the medical terminology. It's not understanding, how to use this machine learning predictor. This is something that I think you could tell family members who don't have a machine learning background about. This is something you could tell juries about. This is something you could tell medical experts about. This is something that you can talk to people about. Whereas I think it's a lot harder to explain what's the output of neural nets, for instance. Conversely, with decision trees, we're not going to have as much predictive power. I mean, they're just not as flexible as some of the models that we've seen elsewhere. With random forests, we can get that predictive power. Even though it's built from these tiny decision tree blocks, you actually get a huge amount of flexibility by having this ability to average over a lot of decision trees. But you lose basically the interpretability of decision trees, because you're not just making this, simple series of decisions anymore. You're making tons of them. And what does it mean to average over tons of these decisions? It's not as clear. And so you get a real trade-off, and it depends on what you're trying to do. Okay, great. Then I hope you all have a great break. I think we won't see each other for a couple of weeks, but I hope you enjoy the Thanksgiving break. And I'll catch you at the next lecture.